Okay, so for the first kind of like warm up thing that I wanted to do, yeah, where is everyone? I feel that. Yeah, so since it's just the two of you, for now, hopefully, um, just go ahead. I wanted to have you fill out this little chart. I think it is going to be super helpful on your index cards that you can have. So if you just want to take a second to figure out which formulas go in which box, and then hopefully some more people will show up in the next couple of minutes. Okay, looks like it's gonna stay small, at least for now. So let's fill this in real quick. Um, all right, so did any of you uh, fill in this box?
Yeah, I have it, Stephen.
Okay, what did you fill it with?
The first one, first left, top corner, yeah. It would be ordered list.
Yeah,
Uh,
ordered list. Okay, and then what about down in this bottom right corner?
that one, no repetition, no order. It should be set.
Yeah, so I'll put set slash combination. Okay, and then what about the top right?
Unordered list.
Yeah, so we'll just put B for bag, and then that
Oh,
leaves this bottom corner as permutation. Okay, so yeah, this will be super helpful. If you don't already have it on your index card, I would definitely recommend it because that was like the most helpful thing when I was taking this class.
yep.
Okay, so since there's so few of you, you kind of have a lot of power here. My plan was to let anyone who's here pick if they have any. We've got review problems and we're going to go over the practice quiz. So if there are any practice quiz questions that you want to go over the solution a little bit more, or if you just want to go straight to extra review problems, it's kind of up to you.
So I've solved the quiz practice problem, but
Mm-hmm.
then I realized that I could do like, so the problem number 2D, I solve it using like the experience that I've had on like the lecture and stuff. Then I
Mm-hmm.
realized like the formula that I used didn't really match the thing
Okay.
given, like the actual formula given. But yeah, the solution is right, but I just wonder like why is it right?
Yeah, okay, so let's go to problem number 2, and we'll just do all the parts. So, okay, so we start with, we've got a bag problem, and we have 5 types of fruit, and we want to fill the bag with 15 pieces. So the first question asks, what is the binary sequence of length 19 that represents a bag with specifically 8 apples, 0 bananas, 2 oranges, 1 lime, and 4 lemons? Okay. So there are actually 2 different answers for this one. It depends what you use to represent the fruit and what you use to represent like the lines or the when I took it, it was explained as stars and bars. I don't know if you've heard of that method, but
Right.
depending on how you do it, you can either start with ones or start with zeros. So let's do it with ones first. We want to represent 8 apples. So we make 8 ones, 6, 7, 8, and then we separate it with a 0. And then we have 0 bananas, so we don't need a 1 for that, but we still want to separate it with a 0. And then 2 oranges and separate it with a 0. And 1 lime, separate it with a 0, and 4 lemons. And that comes out to our 19 characters, or binary sequence of length 19. And then what is going to be the inverse of this? What would be another possible answer?
That would just switch between 0 and 1, right?
Yeah. So 8 zeros, 6, 7, 8, then 2 ones, 2 zeros, 1 0 1 0 0 0 0. Okay, so both of those are just fine. All right, moving on to B. What is the specific sum equation that represents the same bag as in part A? So usually for our sum equation, we have x1 plus x2 all the way up to xn equals r. So in this case, each of these values is going to represent how much of we have of one type of fruit. So we have 8 apples plus 0 bananas plus 2 oranges plus 1 lime plus 4 lemons. And does that come out to, do we put 15 or 19?
Should be 15.
Yeah. All right. Are there any questions on those parts?
No, I have a question on part C and D.
Sorry, you cut out a little bit right there.
Oh, sorry. I have questions on part C and D.
Okay, so let's move on to those. All right, so how many ways are there to fill our bag? So we can use this equation that we just set up.
Sorry, I couldn't see your screen. I couldn't see you writing new stuff.
Oh, man, it's been doing that so much lately.
Right.
Okay. Let me stop the share, try and set it up again. Yeah, definitely let me know if it is doing that, so thank you. Okay, let's try again. Okay, so we can use this formula that we put together. So in this case, we have 5 types of fruits. So we have x1 plus x2 plus x3 plus x4 plus x5 is where we're going to stop, and it comes out to 15. So 5 is our n, 5 is our n, and 15 is our r. Okay, so now we want to use the bag formula, which is n plus r minus 1. Choose r. And that becomes 15 plus, let's keep it consistent. 5 plus 15 minus 1, choose 15. And that will end up being 19, choose 15. And what's another form that we could put this answer that would be the exact same?
Yeah, now it makes sense. So what I usually do is it's not like 19 choose 15, but I do like 19 choose 4, which is the same, right?
Yeah, exactly. 19, choose 4.
So I forgot about that, and then it made me think like, where did the 4 come from? I was like, it
Yeah,
looks
so
right, but it doesn't make sense to the formula.
yeah. So with combinations, and this is only for combinations, it won't be the case for permutations. For combinations, if the R value adds up to the N value, then it'll be the same. So 15 plus 4 is 19. So we can either choose 15 or choose 4 because of the way that combinations work. Because our formula is always going to be N factorial over R factorial n minus R factorial. So in both of these cases, we'll end up having 19 factorial over 15 factorial 4 factorial. And it doesn't matter which one, it'll still have the same formula. Okay, I'm going to erase some of this and move some of it. Okay, so part D. How many ways are there to fill our bag such that we get at least one type of each fruit? So this is similar to the examples that we had in lecture. So we usually have, I'll just copy this formula down. Okay. How do we adjust this formula to match that we have at least one type of each fruit?
I think you can subtract 5 from
Yeah,
15.
exactly. So we just assume that each of these is at least one bigger, so we have to take that away on the other side. So that comes out to 10. And then we can use the same formula as before, except now instead of 5 plus 15, we'll have 5 plus 10 minus 1. Choose.
Excuse me, Zoe, I think your screen is frozen again.
Yeah.
Goodness. Okay. I'm going to try to restart it one more time. And if it still is having issues, I'm going to see if I can attach it with a cable instead. But I usually have problems with that. Okay. Where were we? Okay, yes. We're doing this formula. So this ends up being 14 choose 10, which is the same as 14 choose 4. Okay. Does that make sense to everyone? How we got those answers?
Yeah.
Okay, awesome. All right, any other practice quiz problems that we want to go through? Okay, if there's not anything specific, then I think I'll just go through the review problems. And if you have any questions about the practice quiz problems, feel free to put them in. But since you've already gone through those and looked at those, I assume it will be more helpful to go through some new problems.
A question related to the exam. Is it gonna be like a similar amount of problems like in the practice quiz?
No, it will be considerably shorter than the practice quiz. I think
Right.
that there was some confusion on that since the practice quiz has, I think, like 12 problems or something. It's really big. But don't worry, we'll make sure that it's going to be much shorter than that. Okay, so since you haven't tried these problems before, I'm gonna give each of them just a couple minutes for you to kind of think through and work through on your own, and then we'll walk through them together. And feel free if you're working on it to ask any questions in the chat or just unmute yourself. Okay, so without replacement means that once you draw a card, then you don't put it back. So if you start with like 10 cards, let's say, and you draw one, then now you are only picking from 9 cards. But in this case, it's 52 cards. All right, I think let's get started on this one. Okay, so when we see expected number, it usually means that we're going to have a few different probabilities to work out. So we want to split it into cases based on how many aces there are. So what are our cases for this problem? Okay, so we want to make sure that we consider every single possible number of aces that we can have. So if 5 cards are drawn from a deck, then we can either have 0 aces, but that's going to end up not being used in the problem since it's expected number. So we'll start with 1 ace, 2 aces, 3 aces, 4 aces, and do we include 5 aces?
We cannot.
Yeah, because there's only 4 in the deck total. So these are our 4 probabilities that we want to figure out. Okay, now for each of these, we want to figure out what the probability of them is. So let's start by finding how big our sample space is, since we'll use that as the denominator in all of these cases. So the size of our sample space is going to be, just without thinking of aces or anything, we're just figuring out how many ways are there to draw 5 cards from a deck without replacing them. So what's the formula for that going to be?
Maybe P52 5.
Yeah. Because we don't really care what order they're in, we just care that we can't have repeats. So we use the combination formula. Okay, so now let's look at if we have 1 ace, we know that our denominator is going to be 52 choose 5. All right, so how do we make sure that we only pick 1 ace? So let's think of it as, first we need to figure out which of the aces we're taking from the deck, because there's 4 of them. So let's first choose, out of 4 of the aces, we want 1 of them. But then we also still have to choose the other 4 cards. So now we want 4 cards. And what is our end value for this? How many cards are we picking out of?
51.
Close. So we do need to adjust it for the fact that we drew a card, but the other important thing is that we want exactly one ace. So if we count 51 cards, then we could possibly choose another one of the 3 aces. So we're actually going to pick out of 48 because that's all the cards that are not aces. Okay, so now let's go into if there's 2 aces. We have 52-5 on the bottom, and it'll be very similar. We still want to pick our 2 aces. And then what's this combination going to be to pick the rest of the cards?
Forty-eight. 48 choose 3.
Yeah. 48 choose 3. Okay. I think I'm going to do 3 aces here instead. And we'll just erase these. Okay. Over 52-5. And it'll be similar. Again, we want to choose 3 aces, and then we want to choose the remaining 2 cards. Okay, and then the last one is we want 4 aces. So we'll put this in the denominator, and what is our numerator going to be? So in this case, there's only one way to pick all 4 aces. So we just need to pick the very last card. So we'll do 48, choose 1. Okay, so now how do we use these probabilities in the expected value?
I think we have to time them with their. I'm not sure.
Yeah, there's multiplication, so you're partway there. So we just want to multiply each of these probabilities by their like value. I'm not totally sure that that's the right term, but if there's 1 ace, so we multiply the probability of getting 1 ace by the number of aces. So we will have 1 times the probability of 1 ace. Actually, I'm going to write that differently. 1 times the probability that we get 1 ace plus 2 times the probability that we get 2 aces plus 3 times the probability of 3 aces and 4 times the probability of 4 aces.
Can you explain why we time it with the like 2, 3, 4, the aces?
Yeah, so let's see. So this is the definition of the expected value, or actually I'll write it in brackets. And basically the formula for the expected value is that we're going to multiply it by whatever x is, and we multiply it by the probability that x equals that value. So let's actually call this one, let's call this xi. Okay, so for expected value, we always want to say, okay, here's what it could be, and then we multiply it by the probability of getting that outcome. Does that make sense? And this is also how you would get like the average. So this tells us the average number of aces that you can get when you draw 5 cards from a deck without replacement. Okay, So this would be, as long as you designated that this is the probability, like this is the probability of getting 1 ace, this is the probability of getting 2 aces. As long as this is designated within your problem, this would be a totally fine solution. You don't need to multiply it out or anything. Out of curiosity, did anybody find the final value? Okay, so it ends up being 5/13, which is about 0.385. And that makes, let's see. So yeah, that makes sense to us because the probability of getting even 1 ace is among 52 cards is kind of low. So it makes sense that the average number would be less than 1. And it can be sometimes helpful to multiply these out, but you won't always have time on the quiz since you can't use calculators. So if it's like an easy formula, I would say, and if you have some time at the end, then go back and kind of multiply it out and make sure that it makes sense given the context. But if you don't have time, you're probably better off leaving it in this kind of form. Okay. Are there any questions on that? Okay, let's move on to the next problem. Okay, this one is, at least I think, really cool because there's a couple different ways to do it. So we have an organization with 8 math majors, 12 computer science majors, and 6 science majors. And we want to figure out how many ways you can elect a president, a vice president, and a secretary. Okay, so for A, I'm just going to ask, should we use a permutation or a combination? Okay, this one's a little bit tricky, and the reason is that you can use both. So even though a lot of times there's only, I don't know, there's not usually one way to solve these problems. There's not always problems where you can do permutations and combinations. They're usually kind of separate. But in this case, we can do both. So let's start by using permutations. And the reason that you can use permutations is because it's kind of ordered in this case because we have a president, a vice president, and a secretary. So the assumption is that we're filling in 3 spots, president, vice president, and secretary, and we're filling them in order. So if we use a permutation for part A, the 3 officers are all the same major, means that we have 3 cases. We can either have all 3 officers be math majors, all 3 computer science, or all 3 science. So we want 8 out of the 8 math majors, we want to choose 3. Or we could have 12 computer science majors and choose 3 of them. Or we could have 6 science majors and choose 3 of them. Now, do we add or multiply these terms?
Have to add them.
Yeah, because they are individual cases and they're disjoint. Okay, so that's one way to do it. How would you solve it with combinations?
You just have to change from P to C.
Yeah.
But I guess the answers won't be the same, right?
You're right. So how do we adjust this formula to make it consider the fact that we have positions.
think we have to time it with I don't know, with something.
So we're gonna have some constant out on the side. And we are considering a president, a vice president, and a secretary. So let's see. So in order to consider each of those cases, we're going to multiply it by 6. Because we've got, let's see, president, vice president, and secretary. Is that right? Okay, I believe it is right, but
So what I think of that is like a person has 3 spots to choose from, and then if one person picks one spot and then there are only 2 left.
yes, you're correct. So I think that is 3 factorial, which comes out to 3 times 2 times 1. Thank you. Okay. So let's point down there. And both of these are going to come out. So yeah, these both come out to 1776. Okay. So next, let's do part B. At least one of the officers must be a science major. And let's solve this one just with permutations, and then we'll do C just with combinations so that we don't take too much time on these. Okay, so if we solve part B with permutations, what are we going to do here? What do we start with? Okay, so a hint here is that we have at least one. So if you see at least, you should definitely consider using rule of complement. That's not always the case because sometimes there's fewer cases. You know, like if you're on a number line and the max is 10 and the minimum is 0, and the question says at least 8, you want to just go directly and find 8, 9, and 10 because there's fewer values over here. But if you have at least 1, then you would have to find the probabilities for 2, 3, all the way up to 10. So it's a lot easier just to find the probability of getting 0 and subtract it. So just be careful when you're using rule of complement that you're not overcomplicating things. Okay, so for part B, let's use the complement in this case because it's at least 1, so it's a lot easier to just find the 1 value. Let's find the probability that none of the officers are science majors. Okay, so we still want to use the permutation. If we want none of the officers to be science majors, we're still going to be picking 3 officers. So we still have 3 as the R value. But we do want to adjust the N value because we're no longer including the science majors in what we're counting. So what are we going to put there?
20.
Okay, and now we have to subtract it from the total number because of the rule of complement. So how many ways are there to just pick any of these positions? So no requirements. How would we pick 3 officers?
$26? Is it 26? Yeah.
So we subtract subtract the probability that none of them, or I guess this isn't the probability that none of them are science majors. That was incorrect. It's more like the number of ways where none of them are science majors. So sorry for that confusion. And that is going to come out to 8760. Okay, moving on, let's go to this last part, which is the trickiest. So in this case, we have either the president or the vice president must be a math major. So we want to include, if either the president or the vice president must be a math major, then we want to consider that the president is a math major, or the vice president is a math major, or both of them are math majors. So we could either, because of the inclusive-exclusive principle, we could either count up all the ways that the president is a math major plus all the ways that the vice president is a math major and subtract their overlap, or we can calculate how many ways we get the president is a math major and specifically the vice president is not, or vice versa, and then add their overlap instead of subtracting it. That's kind of confusing, but I think it's easier to think of it like a Venn diagram where this circle represents the cases where the president is a math major, and these are the places where the vice president is a math major. So we'll count up all the ways that are in just this circle. So don't include this middle section. And then we'll add up everything in the right section, still not in the middle section, and then we'll add in the middle section. Okay. So how do we figure out how many ways can we pick a VP, or let's start with president. Pick a president that's a math major. And vice president is not a math major.
It's frozen again. The screen.
Oh shoot. Okay. All right. Go ahead and think on that for a minute. How many ways we can pick a vice or a president who's a math major and a vice president who is not a math major. And I'm going to see if I can figure out another way to connect this screen for a minute. Okay, sorry for that. I ended up having to go get my hub and all kinds of technical difficulties, but it's plugged in with a cable now instead of through Bluetooth, so hopefully it will be a little bit more reliable. Okay, so how many ways can we pick a president to be a math major? So first we want to pick the math major. So out of 8, we want to pick just one of them who is going to be our president. Okay, and then what do we want to do next?
Then pick vice president that's
Excuse me. Yes, pick a vice president who's not a math major. Sorry, not P. So we still want to pick just one to be our vice president. And what is the pool that we're picking from?
CS and science major. 18.
So that will be 18. Okay. And then finally, we want to pick the secretary. And the secretary can be a math major. So now we're just picking out of all the total, sorry. We're picking out of the whole pool of everybody, but we don't want to include the people that we already picked to be president and vice president. So we're going to have, the total was 26. So now we're going to pick out of 24 people and choose one of them to be the secretary. Okay, and this comes out to 3456. All right, now we want to figure out how many ways to pick a president who's not a math major and a vice president who is. All right, we're going to do really similar formula here. In fact, it turns out to be pretty much the same. It's only different in how we write it. So this time we're going to first pick our president out of everybody who's not a math major. And then we want to pick the vice president out of only the math majors. And then we want to pick the very last, the secretary. So that is also 3456. Okay, now the very last thing that we have to pick is we want the president and VP are both math majors. So out of the 8 math majors, we want to choose one to be the president. Okay, now we want to pick the VP. So how are we going to do that?
Is it 7 choose 1?
7 choose 1. And now again, we'll want to pick out of everybody else. And that comes out to 1344. Okay, so in this case, we know that we want to add these two for sure. But are we going to subtract this term or add it? And think of the Venn diagram that we've got up here.
Are we going to add it?
Yes. So we end up with 3456 times 2 plus 1344. And that comes to 8256. Okay, any questions on that one? All right, let's move on. So this time we have a softball player gets a hit with probability 3/5 each time they step to the plate. In any given game, the player has exactly 5 plate appearances. What is the expected number of hits per game? Okay, this one seems like we're gonna split it into cases. It seems like we should split it into how many hits and do Bernoulli trials, but there's actually a simpler way. So if you have 5 trials, each of them are independent of each other, then we can actually calculate the expected value, because essentially the expected value is the number of trials times the probability of a success. So in this case, since we already have the probability and the number of trials, we don't need to calculate anything else. So we can actually just plug in how many trials do we have? 5, yeah. And what's the probability of a success? Yeah, 3/5. So that comes out to 3 is the expected number of hits per game. Okay, any questions on that?
What would be the difference in a problem where you do Bernoulli trials versus this one?
Yeah, so it depends on what the problem is asking you. So like for example, if it asks you the expected number of wins in like a best of 7 or something like that, then we can't use that directly because probabilities will change based on, we've got the 4 blanks and yeah, do you know what I'm saying?
Yeah, that makes sense.
Okay, yeah. So in problems like that, we can't use this straightforward method. And in problems when we don't, like if we have if we're trying to find the expected number, but we don't know the probability yet, then we would have to calculate it like the one that we did earlier. So this can only be used when we want to make sure trials are independent. That's important. Then we also want to make sure that we know for sure exactly how many trials there will be. And we also want to know the probability of success. And these two are where the best of 7 game kind of fails, because the trials are not independent of each other. Winning one game affects whether or not we can win the next one. And we also don't know exactly how many games there will be each time. So this only works because we know there will be exactly 5 plate appearances with probability 3/5. Okay. So let's look at this one. This one's kind of tricky because I'm not sure how much we've gone over conditional probability in lecture. I think there's only been 1 or 2 examples of it. So we have a blackjack hand, and we deal 1 card, which is face down, and we have a second card, which is face up. And T is the event that the face down card has a value of 10, and A is the event that the face up card is an ace. So we want to calculate the conditional probability, which is that the probability that a face down card has a value of 10, given that the face up card is an ace. So when we do conditional probability, we are basically narrowing down our sample space. So instead of picking out of the whole deck, we want to pick out of specifically the fact that the face up card is an ace. Okay, so the actual formula for this, probability of T given A, is the probability of T and A over the probability of just A. And this is what's kind of making our sample space be a little bit smaller. So let's first find what's the probability of that this face up card is an ace. So this is basically like saying we have 52 cards and we have 4 options, 4 ways to get an ace. So there's 52 ways to pick a card, 4 ways to pick an ace, so the probability is 4 over 52. Now we want to figure out the probability that the face down card is an ace, or sorry, the face down card has a value of 10, and the face up card is an ace. So first we have the probability that, the probability that the first card is an ace, the face up card is an ace. And then we also want to consider that the face down card has a value of 10. So now we're picking out of 51 cards because we already picked the ace. And how many of those cards have a value of 10?
16.
Because we've got 4 different cards, 4 different cards and 4 suits. So then when we put these over each other, we'll have 4 out of 52 times 16 over 51 over 4 out of 52. And these kind of cancel out, so we end up with 16 over 51. Okay, part B is a little bit easy since we pretty much already figured it out, but we want to calculate the probability of T and A. So we can just take that from our part A times 16 over 51 is the probability of T and A. So another way to figure out A without having to find this probability, without having to find that probability, is that we just say, okay, so if the face up card is an ace, we know that, then there are 51 other cards in the deck, and 16 of those have a value of 10. So we can just go straight to 16 over 51. But I think it's good for you to get practice using this formula and also just knowing what conditional probability means. So are there any questions on that? I would expect some.
I just was wondering, so are we allowed, in this case, I thought that you have to pick the face down card first and then the face up card. And in that case, wouldn't the second probability not be over 52? Picking an ace.
Yeah, so in that case, if we were to pick the face down card first, let's go ahead and say that we do. So then the probability of that will be what? Probability that the face down card has a value of 10.
16 over 52.
Yeah. And then for the next one, we will still have 4 options, but we'll have 51 cards. And so what this turns into is 16 times 4 over 52 times 51. And that's actually the same as this, which is 4 times 16 over 52 times 51. So because picking an ace doesn't affect whether or not you can get a value of 10, then it doesn't really matter which one you do first.
Okay, that makes sense.
Let's go on. This one is pretty straightforward. How many 5-digit numbers have all distinct digits and are odd? So I guess I should clarify. It seems straightforward, but it might be a little bit trickier. So let's see. We have 1, 2, 3, 4, 5. We have a 5-digit number, and every single digit needs to be different, and the number needs to be odd. So I'm going to let you go ahead and think on this one for a minute. I could be wrong, but I think that there's a lot of different ways to do this problem, like more than usual. So I'd be interested to see what you come up with, and then I'll share the solution that I've got. So until 11, go ahead and work on this. All right, so let's see. In the chat, we've got 5 factorial, and I think that that's a really good guess. In a lot of problems, that would work because we would have 5, or let's see. Actually, I'm curious. Oh, wait, yes. Yeah, I think so, because it would end up being 10 factorial over. Yeah, would you explain actually how you did the 5 factorial? Because I'm curious.
Actually, I just thought of like how many odds numbers are there. So there are 5 out of 10.
Oh, okay. All right. That works. That is a little bit underrepresentative because the only requirement for it to be an odd number is that the last digit is an odd number. So these spots all have a lot more options than
Okay.
this.
Right. I thought all numbers have to be odd.
Yeah, okay, that makes sense. That's something that we would make sure and clarify better on the quiz. So yeah, in this case, it's just saying how many 5-digit numbers have the digits are distinct and the number itself is odd. Okay, so let's first pick an odd number for the last digit. And there are 5 ways to do that. So we'll just put 5. Okay. And then we're gonna multiply because these are all in the same case, because we're saying first we want to pick an odd number and we want to pick something else. So that is either 1, 3, 5, 7, or 9. Okay. And then let's go back to the first digit. And there's actually a slightly smaller number of options here as well. So we can have anywhere from 1 to 9. And why can't we pick 0?
Because then it's not a 5-digit number.
Yeah. So in this case, we have 9 options. Or sorry. Not, oh wait. Why can't, oh, they're all distinct, sorry. So yes, so we usually would have 10 options, but we also have 1 less because each of these have to have distinct digits. So this one we have 8 choices. Okay, and now for these 3 spots, we can have anywhere from 0 to 9, but we can't include numbers that we picked before. So how many options do we have to fill in this blank?
Also 8,
Oh,
And then the next one?
7.
Yeah, and then down to 6. And this comes out to 13,440. Okay, are there questions on that? Did either of you figure out a different way that still works? Okay, that's totally fine. I was just curious. Okay, let's go on to, actually, let's see. Sorry, I got confused. My iPad is showing that it's 9:41 on January 9th. So, don't know why that is. I was like, it's not 9:41, it's 11. Okay, I'm just gonna give you both, you can choose to take it or not since it's just the 2 of you. Usually with the 2-hour review sessions, I do like a quick 5-minute break in the middle since it's kind of a lot all in one sitting. So do you want to take a 5-minute break or just keep going?
Yeah, that sounds good.
Okay, so we'll come back at 11:09-ish. Let's just make it 11:10. And yeah. let's get back to it. And looks like we have a couple more people than before, so welcome. We are just going through the extra review problems right now, but if you have any specific questions you want to go through on the practice quiz, you can go back up to those and review them. Oh shoot, you were in the wrong link. Oh, sorry. I answered a question on Piazza this morning asking about that, so I was hoping people would see it, but luckily I've been streaming it on YouTube, so you can watch the first half later. Okay, so we want to find out what is the probability that in 10 tosses of a fair coin, the result of heads appears at least 8 times. So this is one of those where we see at least, and we consider rule of complement, but it's actually going to be more work to do it. So let's just find it directly. So we have the probability. First, we want to, if we have probability, first we want to find the size of the sample space. So we want to figure out what is the total number of outcomes that we can have if we have 10 tosses of a fair coin. So how do we figure this one out? So no matter what, we're going to need, 2 to the 10th. Awesome. 2 to the 10th, which is 1024. Okay. So now we want to figure out the E value. So let's see. We want to figure out how many ways we can get 8 heads, 9 heads, and 10 heads. So how are we going to pick these? If we want 8 heads, then how do we figure out how many ways there are to get 8 heads in 10 tosses? So we can kind of, let's see. Bernoulli trials are actually a little bit more complicated than we really need, just because the probability of getting a heads and a tails is the same either way. So let's think of it as we have 3, 4, 5, 6, 7, 8, 9, 10. We have 10 blinks that we're filling with either heads or tails. So if we want heads to appear exactly 8 times, we just need to pick 8 of these slots that heads are going to go into, and automatically the tails will fill in afterwards. So we actually can use the combination formula, and out of 10 spots, choose 8. All right, and then for 9 heads, we do the same. 10 choose 9, and then 10 choose 10. Okay, so all of our probabilities we're going to have, let's see, 10 choose 8 comes out to, let's see, it'll be 10 factorial over 8 factorial times 2 factorial, which is 10 times 9 over 2. And we can cross it out, so it'll be 45. All right, let's figure out 10 factorial over 9 factorial is just going to end up being 10. And 10 choose 10 is just going to end up being 1. Okay. So we have 45 over 1024 is the probability of getting 8 heads. This is the probability of getting 9 heads, and this is the probability of getting all 10 heads. So do we multiply or add these? Yeah, we'll add them. And so it comes out to 56 over 1024. And you can totally leave it in that form. You can also leave it in the form if you put 10 choose 8 over 2 to the 10th and so on. That would also be totally reasonable. You don't have to multiply any of these out, but I was saying earlier, it can sometimes be helpful to make sure that you get an answer that makes sense.
The practice quiz, it was saying that you had to write out like the multiplication for the combinations and permutations. Is that what we're doing for the quiz? Or is that just for the
we'll make sure
practice
and
quiz?
specify on each problem. Yeah, we'll make sure and specify on each problem. There will be some problems that we want you to get it into this form. And you don't have to go further than that, but that's just to make sure that you know what the permutations and combinations are doing. So yeah, make sure that you know how to get from here to here, or if we had a permutation, that you know how to get from here to, I believe it's just going to be 2. That you know how to get from here to here. Because there might be some questions that will ask you to do that.
But it's
Okay.
not every question.
Yeah, it'll depend, because like for something like if you had choose 450 and like, actually I think permutation would be a better example of this. If we had a permutation of like 450 choose like 25, we wouldn't ask you. And also this might, yeah, I don't know. There's some problems that it might be difficult to get it into that form. So if there are problems like that, we wouldn't ask you to do that.
Okay. Thank you.
Okay. Next problem. All right, we want to elect a chair for a committee among 20 students, and there are 4 candidates for the chair. How many ways can the votes come out? Okay, this one's a little bit tricky to wrap your head around. So I'm just gonna give you like 1 minute to kind of think through this and see if you can think of a possible solution, and then we'll come back together. And feel free to ask questions in the next minute or so.
We're electing one chair.
Elect a chair for a committee among 20 students. Yes. And there are 4 candidates. And so when it says how many ways can the votes come out, it's saying how many ways can each candidate get votes. Like if there were like 100 total votes, how are we distributing those 100 votes to each of the 4 candidates?
So is each person in the committee vote once?
Yes.
So 20 votes among 4 people.
Mhm. Okay, so let's go through this one. First, let's figure out what formula we want to use. So are repeats allowed? Like as in, I guess let's first think of what we're picking from, what we're selecting. So we basically have 4 blanks, and each of these blanks is going to have a certain number of votes for each candidate. So when we're asking for repeats, we're saying, can 2 candidates get the same number of votes? Yes, exactly. We can use it, we can treat it like a choose fruit problem or a bag problem. So yeah, so repeats are allowed and order doesn't matter, which is why we can use the bag problem. Okay. So there's our formula, and we need to choose our n value and our r value. So what is our n going to be? Yes, exactly. 4. And our r value? Yeah, 20. Because it's like having x1 plus x2 plus x3 plus x4 equals 20. Okay, so now let's plug it in. So we get 20, sorry, 4 plus 20 minus 1, choose 20, which comes out to 23, choose 20. And this could also be 23, choose 3. Okay, awesome. So are there any questions on that?
So I guess that means you could have nobody vote in that case.
Yeah, well, so we wouldn't have nobody vote, but it would mean like one person could get 0 votes. And then the others would distribute the 20 votes between them.
Okay.
All right. So that is actually the last review problem. The rest are all from the practice quiz. So again, I'll kind of leave it up to you. Do you want to go through the practice problems and just review some of those practice quiz solutions, or are there any other questions that you have specifically that we could go through from homeworks or discussions or anything? Okay, if no one has a preference, then we can just go through the discussion or the practice quiz problems. Just since we've already got those ready. Yeah. So let's come back up here, and we've got about 40 minutes, so we'll just go through, and feel free to, if you do have any questions come up, just go ahead and let me know, and I can do that problem instead of the next practice quiz problem. And then if you've already gone through the practice quiz and you don't have any questions, then feel free to take off, but otherwise, let's go through. Okay, so we have a suitcase with an ordered 4-digit combination lock, and we want to first figure out how many possible combinations are there. So again, let's ask, are repeats allowed? Can we have the same digit twice?
Yes, you can.
Yes. And then does the order matter?
No.
Can you explain why?
No, I guess it does matter.
Okay, yeah. So when it asks if the order matters, it's basically saying if we get these 4 numbers, are we considering them just a set, or did they have a sequence? So since it's an ordered combination lock, and like if we had 4 1 3 2, that's different than 1 4 3 2. Those are two different combinations. All right, so in that case, we will use an ordered list, and we want to find an n value and an r value. So how many options do we have for each digit?
And
And we are picking 4 digits total. So we have n to the r equals 10 to the 4th. Okay. Now B, counting the number of possible combinations, we kind of already figured this out since we used it to do the problem, but let's see. So we're using an ordered list. All right, next part. How many possible combinations have distinct digits? So the difference here is that it's still ordered, but now we can't have repeats. So what are we going to use? All right. Let's actually think of this a different way. Let's see. We have 4 slots, and each of them have distinct digits. So for this first option, for the first blank, how many ways can we fill in the first blank?
Um, 10.
Yeah. And for the second one, since we can't have repeats, we'll have 9, and then 8 and 7, and this comes out to 5,040. Okay, so we didn't really use any of these, but if we were to use an ordered list, permutation set, or unordered list, which of them would get us the same answer?
Permutation.
Mm-hmm. And the formula for that would be, we have 10 and we're picking 4, which would turn out to be 10 factorial over 6 factorial, and that would get us the 10 times 9 times 8 times 7 that we got here. All right. So now we want to figure out how many possible combinations have 7 as the leftmost digit. So we have 4 blanks, and we pick 7, and now we still have 3 more blanks to fill. So how are we going to fill those blanks?
Do the 3 ways.
Yeah. So there are 2 ways to do it. We can either say, okay, first we pick the first one, there's 10 options, and then 10 options, and then 10 options. Or we can just use an ordered list and say that we're picking from 10 options and filling 3 blanks. But either way, our answer is going to be 10 to the 3rd, which is 10,000. I should really know this. One of those mornings. 1,000. Don't tell anybody that I could not figure out 10 to the 3rd. Okay. F. Okay. So now how many possible combinations do not have 7 as the leftmost digit? So again, there's a couple different ways to solve this. Does anybody want to say how they would figure it out? Nine times 10 to the 3rd. Yeah, exactly. So I assume what you did, 2, 3, 4. Also, that looks like an A. Let's try that again. Was we have 9 options here to fill in with a 7 because we don't want a 7, and then we can choose anything else for the other 3, which is 9 times 10 to the 3rd. The other way that we can figure it out is using the rule of complement. So we know that the total number of ways that we can, let's see, where was it? 10 to the 4th. So there's 10 to the 4th total possible combinations minus 10 to the 3rd for combinations that do have 7, which ends up being 10,000 minus 1,000, which is 9,000, and that is also equal to 9 times 10 to the 3rd. Okay. Did anyone figure it out any different ways? I'm sure there are other ones. Okay. Still on the suitcase problem, now we're asking how many possible combinations have an odd number as the rightmost digit. So we have 4 blanks, and this digit has to be either 1, 3, 5, 7, or 9. So in this case, we're going to have still 10 options for each of these blanks, but now we only have 5 options here. So we end up with 5 times 10 to the third. All right, and then for H, how many possible combinations have 7 as the leftmost digit and an odd number as the rightmost digit? So now this has to be 7, and this has to be 1, 3, 5, 7, or 9. And these can be anything. So what does that come out to? Okay, so let's see. 10 squared, 10 squared times 5. Let me see if that, 10 squared times 5. Why does that not work? Oh wait, I was looking at the wrong thing. Yes, you're right. 5 times 10 squared. All right, this is where we're gonna have to figure out a couple other things. So now we want to figure out how many possible combinations have 7 as the leftmost digit or an odd number as the rightmost digit. So we know that the number of combinations that have 7 as leftmost, is equal to, we said 10 to the third. And an odd number as the rightmost digit is 5 times 10 to the third. All right, and then what else do we need here? What are we missing? Yeah, exactly. We need to subtract that 7 is leftmost and odd is rightmost, which is 5 times 10 squared. So we end up with 10 cubed plus 5 times 10 cubed minus 5 times 10 squared, which is going to be 1,000 plus 5,000 minus 500. And that comes out to 5,500. Okay, does that make sense to everybody how we got there? Okay. And then we already did practice problem 2 a little bit earlier. So let's move on to 3. How many distinguishable arrangements are there of the letters in integer? So I'm going to give you just 1 minute to work on this. And again, feel free to ask any questions. Okay, so that is 1 minute. All right, there are a couple different ways to solve this as usual. So I think personally the easiest way for me to do it is to think of this as we've got 7 blanks to fill. 1, 2, 3, 4, 5, 6, 7. And we want to fill them with, we have an I, an N, a T, we have 2 E's, and a G and an R. So this is possibly the brute force way. It's a little bit of extra work, but essentially we are just choosing where each of these letters go. So first we have 7 blanks and we choose 1 for the I. And then because we filled in one of the blanks with an I, then now we only have 6 available. And so we choose 1 for the N. And we basically keep going like that until we get to the E's, which now we have 4 spots available, but we're filling 2 of them. And then because we picked 2 of them, we now only have 2 available for the G, and we pick one of those spaces. And the last one for the R is just automatic. So that's a little bit, that's a lot of stuff to write down. So what's another easier way to do it? So since we have 7 blanks, we can fill it in 7 factorial. But then we also need to divide out the fact that we have these E's, so we can just divide it by 2. Actually, that should be 2 factorial, which is the same as 2. But like, for example, if we had 2 R's, then we would also divide it by 2, or sorry, there were 3 R's, then we would do 3 factorial for 3 R's. And both of these are going to come out to 2520. Okay, are there questions on either of those possible solutions?
Second one that you did works because why does that work? Why does dividing it by 2 factorial work?
That is kind of a complicated question. So basically what this ends up, so this turns out to be 7 times 6 times 5 times 6 times 2. Okay, I believe, let me double check that. 7 times 6 times 5 times 6 times 2. Yeah, okay. So this, the factorial, comes out to 7 times 6 times 5 times 4 times 3. Okay, let's see. I'm going to write that differently because that doesn't look the same as 7 times 6 times 5 times 4 times 3. Okay, so the reason that we divide it by that 2 factorial, because usually we'd have times 2. If we were just doing, if we just had 7 factorial, then we would have this times 2. But we have to divide out the duplicate results. So if we had, if the arrangement that we came out to was, let's fill in E, and then just G, T, R. Okay, if this is the arrangement that we came up with, then counting it this way is counting duplicates, because if we consider this, let's color, that E is going to be blue and this E is going to be pink. And if we switch those, G, T, I, R, N, if we switch those, then these are actually still going to be the same. no matter what. They're still technically the same distinguishable arrangement. That's the important thing. These are not distinguishable from each other, so we don't want to count them. So this dividing by 2 factorial basically just cuts those out. It takes out all the copies that were made that had duplicates like this, where 2 e's were in the same arrangement, but they were counted twice.
And that's because
so that comes from
for every arrangement
this
of
7
e's, there would
factorial
be...
is actually a permutation of 7.
So I was saying for every arrangement of e's, there's another arrangement of e's that looks equivalent. So you divide it by 2.
Yeah, exactly. So it's basically like the permuted results. So 2 factorial is basically like taking a permutation of 2 choose 2. So it's like saying we have, we have E1 and E2, and we're filling those blanks. So we're taking away all the permutations, which are just E2 and E1, and we're dividing them out. But if we had, like I was saying, if we had, running out of space here, if we had 3 R's, then we would divide by a 3 factorial because it would be like finding all the permutations of R1, R2, and R3, and then dividing them out. Does that make sense?
Yes.
Okay, awesome. So yeah, so basically this is a simplified version of all of that math, where we can just take the factorial and then divide it by however many copies there are. All right, moving on. So for this one, we have a club that has 8 sophomores, 5 juniors, and 10 seniors as members. And we want to form a committee with 6 students. And the important thing here is that it's a committee that doesn't have a vice president or a president or a secretary. It's just a committee, so it doesn't matter what order we pick them in. So let's first figure out what N and R are going to be. Okay, what is our N value? Remember that N is the size of the set that we are picking from. So if we're forming a committee out of a certain number of club members, then the N value is going to be the number of club members because that's what we're picking from. So we have 8 sophomores plus 5 juniors plus 10 seniors, which is 23. And R is how many we're picking, which is the size of the committee, so 6. Okay, now which formula are we going to use? All right, let's think about repeats in order. So can we have repeats? Can one student be in the committee twice? Yeah, no. Okay, and does the order matter?
No.
Yeah. So from our chart that we had earlier, that brings us to a set, which means we're going to use combination. So now we just need to plug it in, and we get 23 choose 6, which comes out to 100,947. And again, this would be a totally fine, depending on what was specified in the quiz, that would be a way that you could leave it. But we also might have you put it in the form 23 factorial over 6 factorial, 17 factorial. Okay, now part B. How many ways are there to form the committee if it must have the same number of students from each classification? Okay, so if we have the same number of students from each grade, then, and we have 6 students, then how many can we have from each grade?
2.
Yeah. 2 from each grade. So we want to pick 2 out of our sophomores, 2 out of our juniors, and 2 out of our seniors. Okay, do we use the rule of product or the rule of sum? Yeah, product. Because these are all the same case. We're choosing 8 sophomores or 2. We're choosing 2 sophomores and we're choosing 2 juniors and we're choosing 2 seniors. Okay, and these come out to 28 times 10 times 45, which is 12,600. Okay, next part. How many ways are there to form the committee if it must not have the same number of students from each classification? Okay, so this is one of those times that it's not immediately obvious, but what rule are we going to use? Okay, so which is, yes, complement. Yeah, because looking at this problem, I would think, okay, I can't have the same number of students from each classification, but it's a lot easier to figure out how many ways to find the same number of students from each classification. So we can basically take what we found last time and subtract it from the total number of ways to form a committee. So, and we actually already have both of those numbers. So we found this in part A is the total number of ways to pick a committee. And then we subtract the 12,600 that we got from part B. And that ends up coming out to 88,347. Okay, does it make sense why we did all of that? Okay. So our last problem, what is the probability that a selected committee will have the same number of students from each classification? And again, we've already done the math for this. We just need to figure out how to use it. So what is the size of our event? If the event is that there are the same number of students from each classification.
Is it the 12,600?
Mm-hmm. Okay, and the number of our sample size is going to be what?
Is that the 100,000?
Yeah, the 100,947. So we can just put these on top of each other. And that comes out to about 0.125. Okay, moving on, are there any questions on that? Okay. All right, suppose that an unfair coin gives heads with probability 3/4. So what is the probability that exactly 5 heads come up when this coin is flipped 8 times? Okay. So this is one of those cases where we want to use Bernoulli trials. And the reason that let's see, that expected value, it seems like we have all of those conditions. The flips are independent and the coin has a known probability and we have a known number of flips, but that formula was only for expected number, and this is just asking what the probability is. So what is the probability that exactly 5 heads come up when the coin is flipped 8 times? So there are a few different things that we need to figure out. We need to figure out how many successes we have, which is with K, number of successes. We need to figure out what the probability is, which we actually already have, is 3/4. That's the probability of success. And we also need to figure out how many trials we have. Okay. So what is K going to be? So let's consider that a success, let's just say a success means that we have heads. So if we want exactly 5 heads to come up, then the number of successes that we want is 5. And then how many trials do we have?
Eight.
Mm-hmm. Okay, and now it's not too bad because now we basically just fill in our formula. So the Bernoulli trials, let's see. Yeah, so first out of 8 successes, out of 8 flips, we'll choose 5 that are successes. And then we want to multiply by the probability of a success to the power of 5, because we have 5 successes, and the probability of a failure to the power of 3, because that's the remaining options. Okay, and there we go. We can leave it in this form or we can multiply it out, but we'll just leave it how it is for now. I want to make sure that the Bernoulli trials make sense outside of the formula, because I think the formula is quicker, but it's important to also know where it comes from. So let's just hurry and go through what each of these terms is doing. So essentially we have 8 blanks, and first, this first term, we want to pick which blanks, or I guess I won't call them blanks, I'll call them which flips are a success. So out of these 5, let's just pick, or out of these 8, let's pick 5 that are a success. Okay, and then the rest automatically fill in with tails. So now we are basically saying, okay, so we've picked what each of them are, but each of these have a distinct probability, which is 1/4, 3/4, 1/4, and so on. So we end up having 3/4 to the 5th because there are 5 H's that are giving us 3/4. And then our 1/4 is to count each of these tails, which have a probability of 1/4. So we have 3 tails. Okay, and then that will hopefully help you when we have like best of 7, because those ones are a little bit trickier to figure out since you can't just plug everything in directly. Okay, we have just a few minutes left, so let's see. We've got, out of the remaining problems, are there any that either of you have a preference for solving? Specifically, like if you struggled to do them before you looked at the answers, or if the answer didn't make sense out of 6, 7, and 8. Okay, then I'll just go on to the next problem, and hopefully it'll be a good one that'll help you out. Okay, so we have that there are 2 fair 6-sided dice are rolled, 1 red and 1 green. And we want to find what is the probability that at least one die shows a 2, or the dice sum to a value no greater than 5. So this is one of those rule of sums with overlap where we're going to have to find the probability of each of these cases and the probability of them combined. So let's first find, oops, that's the eraser. First find the probability that at least one die shows a 2. Okay, so we can think of this as, let's see, probability that at least one die shows a 2 is, so we have, let's see, 36 different options. Actually, you know what, here. I'm gonna do this a different way than I've got here because I think it's a little bit easier. Let's first find the probability that neither die shows a 2 and subtract it. So if neither of them show a 2, then we would just have 5 6 times 5 6 because there are 5 faces that don't have a 2, and that comes out to 25 over 36. And then if we subtract that from 1, so the probability of at least one shows a 2 is 1 minus 25 over 36, which comes out to 11 over 36, which I believe is what is showed in the solution. Yes, 11 over 36. So this is just another way to solve it other than what the solution showed. Okay, now we want to find the probability that the sum is less than or equal to 5. So I think the easiest way to do this one is to do it the same way as the solution, which is just to think how many dice sum to a value no greater than, like just count out which options we have. So we can start with 1. 1 and 1 will be 2. And we can go all the way up to 4. Okay, so now let's consider all the options that start with 2. We'll still have 2, 1. And we count both of these because the dice are red and green. So one of them is red, one of them is green, which means that 1, 2 is different than 2, 1. Okay, and then we can have 2, 2 and 2, 3, but 2, 4 would be 6, so we don't include that one. Then we'll have 3, 1 and 3, 2 and 4, 1. So this is 7, 8, 9, 10 total options. So we have 10 out of 36 total possible rules that satisfy it. Okay, now we need to figure out which of these satisfy both. So let's just go through this little sample for us and figure out which one of these shows a 2. So we'll highlight each of the ones that has a 2, and that gives us 5. So the probability of both is 5 over 36. And so the probability that at least one dice shows a 2 or the sum is less than or equal to 5 is going to be 25 over 36 plus 10 over 36 minus 5 over 36, which comes out to 16. Oh, sorry, not 25. That should be 11. Okay, that is, I think, a good stopping point since it's almost 12 and since you're the only one left. Thank you for sticking around the whole time.
Yeah, thank you so much.
Are there any other questions you have before?
No, I think I'm good.
Okay, awesome. Good luck on the quiz tomorrow.
Thank you. Bye.
Bye.